How are you all doing this morning?
Doing well.
Doing
So I had a question from a student regarding homework 5, problem 3. So we're going to start off today by looking at that. So let me share what I've got prepared. So we're going to look specifically at part 3B. 3A, I feel, is actually fairly straightforward and is a reasonably good place to use the superposition theorem. No dependent sources or anything like that. 3B makes things a little bit more difficult, so we're going to talk about it, and then it's actually going to provide a very good segue into our nodal analysis, which is the real topic for today. So in homework 5, problem 3B, we have the following circuit. It has 2 independent current sources and 1 dependent voltage source. So we're going to work the problem with turning off the current source I2 and leaving I1 on, and then we're going to work the problem again with the current source I1 off and I2 on. We can never turn off the dependent voltage source in this case, so that always needs to be left on. So if I1 on and I2 off, what we have is this circuit. I1 prime. Resistor R1 and resistor R2, and here is IY prime. So, and we've turned off our current source I2 by replacing it with an open circuit. So that's why we don't have that rightmost branch with the current source I2. So to solve this for the current IY prime, is going to be tedious, I guess would be the best way to put it. And what I mean by that is that we're going to have to apply both Kirchhoff's current law, Kirchhoff's voltage law, and Ohm's law to develop relationships. So I'm going to call this current here IR1. And we can get a relationship that says that I1 is equal to IR1 plus IY prime, which is the current that we're looking for. And I'm going to call this voltage drop VR1 and this voltage drop VR2, and I can write a Kvl equation, put a line here, where I have negative VR1 minus 5IY prime plus VR2 is equal to 0. So I currently have 2 equations, and let's see, I1 is known, so IR1 is unknown, IY prime is unknown, VR1 is unknown, VR2 is unknown. So I have 2 equations with 4 unknowns. So I'm going to have to come up with some other equations. One equation that I can have is VR2 is equal to R2 times IY prime. And another equation that I can get is that VR1 is equal to R1 times IR1. So if we substitute these 2 Ohm's law relationships back into our second equation, that's going to give us negative R1 IR1 minus 5 IY prime plus R, dang it, my pen thing stopped working, R2 times IY prime is equal to 0. So now I have this equation and this equation, which only have the two unknown quantities, IR1 and IY prime. So I could solve that system. Everybody with me thus far?
Yes, sir.
All right, so I could solve that system of equations, and I could get some numerical value for IY prime. So let's work now the relationships for with I1 off and I2 on. That's going to be resistor, current source direction up. Here we're going to have our dependent voltage source. This is IY prime, double prime, excuse me, minus plus 5 IY double prime, R1, R2, and our known current I2. So it's a very similar circuit, and we're going to have to apply pretty much the same approach. So I'm going to call this current IR1, this voltage drop VR1, this voltage drop VR2. And I can see that I'll have I2 is equal to IY double prime plus IR1. If I write a KVL equation, I'm going to get minus VR1 minus 5 IY double prime plus VR2 is equal to 0. My Ohm's law relationships are VR1 is equal to R1 times IR1. VR2 is equal to R2 times IY double prime. And if I substitute these Ohm's law relationships into my KVL equation, I get minus R1 IR1 minus 5 plus R2 IY double prime is equal to 0. And I have two equations, both containing the two unknown currents, and I can solve for IY double prime. So the second step of this is extraordinarily similar to the first step. So now I can solve for IY prime, I can solve for IY double prime, and I add those results together. Nothing wild or crazy there. The issue that I have with this problem, being a problem used to teach the concept of superposition, is that we had to set up a system of equations to solve it. There was no way around it. And if we're going to set up a system of equations to solve the thing, we might as well just use nodal analysis, which is today's lecture topic, or mesh analysis, which is Monday's lecture topic, and only solve the circuit once. So let me redraw my original circuit. I1, R1, R2, I2, 5IY, where this current is IY. All right, so we are going to solve this circuit using nodal analysis, and we should see that it's actually significantly easier than the superposition method that we employed when we solved it just a moment ago. Even though we'll actually come out with the exact same numerical results, the analysis will be significantly easier. So the first thing that I do in a nodal analysis problem is identify my nodes. So I have this orange node, this green node, and lastly, this blue node. I'm now going to choose which one will be my reference, and I'm going to choose the bottom node because it has the most elements connected to it. Sorry, my dog is being a jerk. Give me just a second. Okay, so now that I've identified my reference node, that is effectively where I'm assuming the point in the circuit that has a potential of 0 volts. So I'm going to label my other two nodes. So I'm going to call this guy node A. And so we'll have a nodal voltage VA. And I'll call this guy node B. So it will have a nodal voltage VB. Let's see. So this circuit contains what's called a supernode because there is a voltage source present in the circuit. And so the supernode is going to be nodes A and B. Or it's comprised of supernodes A and B. Anytime we have a voltage source, we will have a supernode. And for every supernode, there will be a voltage relationship equation. So the voltage relationship equation is determined pretty simply. So whatever nodal voltage is connected to the positive polarity voltage of the positive polarity terminal of voltage source, in this case that would be VB, minus whatever voltage is connected to the negative polarity terminal of the voltage source, in this case is VA, is equal to what the given voltage drop over the source is, which in this case is 5 times the current IY. So that is our voltage relationship. We also have to write a Kirchhoff's current law relationship for our supernode. So KCL at supernode AB, where we are going to be summing the currents that are leaving our supernode. So let me draw what those currents are going to be. Let's use this light blue color. So I'm going to be taking into account this current that's flowing to the left through down through the current source, this current that's flowing down through resistor R1, this current that's flowing down through resistor R2, and this current that's flowing to the right through current source I2. So my current directed to the left is going to be negative I1. My current directed down through the resistor R1 is going to be the voltage drop over that resistor with respect, so that's VA minus 0, so just VA over resistor R1. Then I have the voltage drop, or excuse me, the current flowing through resistor R2, which is going to be VB minus 0 over R2. And lastly, I have the current directed to the right, which is negative I2. Set this guy equal to 0. And my final thing to do is to develop an expression for the controlling variable IY. So this is another equation. and I can see that IY, using Ohm's law, is going to be VB minus 0 over R2. So IY is VB divided by R2. And I now have 1, 2, 3 equations, 3 unknowns, and I can solve for IY directly. So using nodal analysis for parts B and C of problem 3 is actually a much more straightforward method than using superposition like you were asked to do. So any questions thus far?
No, sir.
Yeah, I'm really not a fan of this particular homework problem just because it doesn't make logical sense to me. If you're going to have to set up a system of equations to solve it, you should use one of the circuit analysis methods that involves setting up a system of equations, like nodal analysis or Kirchhoff's current law. All right, so hopefully that was a sufficient explanation for whoever it was that posed that question in an email. If not, let me know and we'll work through more stuff. But let's move ahead to the in-class assignment then.
Which homework problem was that? I can't find it.
Homework 5, problem 3B. That's why it's written up at the top.
Sorry, I didn't see that. Okay.
All right. So the in-class assignment, we're asked to use nodal analysis to determine the quantities V1, V2, and I for the circuit shown below. And it looks like we have already had our reference node selected for us. I will still go through, and our nodal voltage is assigned, but I'll go through and identify the nodes anyway, just to make a habit of it. So this is one node and it has been assigned a nodal voltage of V1. Here's another node and it's been assigned a nodal voltage of V2. And lastly, we have this bottom node, which serves as our reference or ground node. There are no voltage sources present, so we don't need to worry about any kind of supernodes or anything like that. So we can really just jump straight in here and start applying Kirchhoff's current law at our non-reference nodes. So KCL at node 1, we're going to be adding together this current directed to the left, this current directed down, and this current directed to the right. So that will be, the current directed to the left is negative, sorry, that's the wrong color. $10 The current directed down is our nodal voltage V1 minus 0 over 8 ohms. And our current directed to the right is V1 minus V2 over 3 ohms is equal to 0. Then we have our KCL equation at node 2. And I'm going to leave this one for you guys to tell me what to do. But I will specifically say which current portion I'm asking for. So how can I express the current that I've drawn with the blue arrow directed to the left through the 3 ohm resistor in terms of my nodal voltages?
V2 minus V1 over 3 ohms.
Yep, V2 minus V1 over 3 ohms, great. How about this current directed down?
V2 over 4
over
ohms.
V4.
V2 divided by 4 ohms. And finally, this current directed to the right.
-2 amp, minus 2 amps?
Yeah, minus 2 amps, because The current that we're looking for, the current directed to the right and then down through the current source, is opposite the direction indicated. So
Okay.
we'll have a minus sign. So we have two equations, two unknowns. So let's get out our trusty calculators and solve this system. 2 by 2. So the coefficient for V1 on our first equation is going to be 1/8 plus 1/3. The coefficient for V2 in our first equation is going to be minus 1/3. And then our constant term, when we move it to the other side of the equal sign, will be positive 10. And our second equation, our coefficient for V1 is minus 1/3. Our coefficient for V2 is 1/3 plus 1/4. And our constant term, when we move it to the right-hand side of the equal sign, is positive 2. And so the answers that I get are V1 is equal to 41.6 volts, and V2 is equal to 27.2 volts. So how can I use these two nodal voltage values to determine the current I?
You can do V1 minus V2 over 3 ohms is equal to I.
Exactly right. I is V2 minus V1 over, sorry, V1 minus V2. I think you said it correctly and I just got it backwards in my head. V1 minus V2 over 3 ohms. And it looks like 4.8 amperes. So this guy, pretty cut and dry, just basic applying the nodal analysis process, where the initial steps of identifying your reference node and all that kind of stuff were done for you. Any questions on this guy before we move ahead?
I'm good.
All right. So problem 2, using nodal analysis, determine the power supplied by the dependent sources shown in the circuit below. So let's identify our nodes. Alrighty, so that's step 1. Which one of these 4 nodes do we want to serve as our reference?
The
Bottom
bottom.
one.
Okay. That seems reasonable. It's going to make it more boring, but that's okay. So let's see. I'm going to call this left-hand node in orange node A, so it will have an associated nodal voltage VA. This middle blue node will be node B, so it will have an associated nodal voltage VB. And this green right-hand node will be node C with an associated nodal voltage VC. So, do we have a supernode in this circuit?
VB and ground.
Right, okay, so anytime there's a voltage source, there is a supernode. Since there's a voltage source here, doesn't matter if it's independent or dependent, we will be applying our supernode techniques. So we are going to have a voltage relationship equation. So what is our voltage relationship equation going to be?
Would it be VB minus 0 equals 3VX?
Exactly right. So we can just say that VB is equal to 3VX. Do we need to perform Kirchhoff's current law at our supernode?
No, we don't.
That's correct. We do not need to perform KCL because our supernode contains the reference node, and we never do KCL at the reference node. So that is our only relationship that we are going to need for node B. All right. So then we go into our KCL relationships for our non-reference nodes. So KCL at node A. So who wants to start me off with one of those terms?
VA minus VC over 15 ohms.
All right, so that'll be the current directed up through the 15 ohm resistor. So VA minus VC over 15 ohms. All right. Plus. All right. What's another term that we're going to have there?
Minus 2 amps.
Minus 2 amps. Okay, so that's the current directed down through the current source. So the only other branching path is through the 3 ohm resistor. So what's that term going to be?
VA minus VB over 3 ohms.
All right. Over here, let's do KCL at node B. Oh, excuse me, node C, because B is taken care of with our voltage relationship equation. So what are my terms of my KCL at node C going to be?
VC minus VA over 15 ohms.
All right, so that's the current directed up through the 15 ohm resistor. What's another one of our 3 terms going to be?
VC minus VB over 10 ohms.
All right. And what's our last term going to be?
Negative 2 VX. Everywhere where there's VB, should we have put VX or 3VX?
We could. It really just depends on how you want to play this, and we'll talk about that in just a moment. So right now we have 3 equations, but we actually have 4 unknowns. We have VA, VB, VC, and VX as an unknown. So we're going to have to develop an extra equation, which I call other equations, or other relationships, depending on my mood, where we're going to have to express Vx, our controlling variable for these 2 dependent sources, in terms of the nodal voltages. So how am I going to express Vx in terms of the nodal voltages?
VA minus VC.
VA minus VC. Are you sure?
I'm pretty sure, yeah.
Yeah, you're correct. So the reason why I asked you that is I wanted to see if you would bite. A lot of people make a very, very common mistake. So I've seen a whole lot of students say that Vx would be VA minus VC over 15 ohms. So let me write that down.
That's the current.
Exactly right. VA minus VC over 15 ohms. That is the current flowing through our 15 ohm resistor. It is not the voltage drop. I don't know why students make that mistake extraordinarily often, but they do. So I just wanted to point it out so that hopefully we can cut it off, cut off that behavior before it becomes a problem. So sorry, go ahead.
So Vx equals VA minus VC because of the polarity of the terminals?
Exactly right. So VA is the nodal voltage associated with the positive polarity terminal. So that gets the positive sign. And VC is the nodal voltage associated with the negative polarity terminal. So it gets the minus sign. So that's why Vx is equal to VA minus VC.
Okay, thank you.
Mm-hmm. So now we have 4 equations, 4 unknowns, which is technically too much for our little calculators to handle. So we could substitute in Vx is equal to VA minus VC into this relationship and this relationship. And now we have 3 equations, 3 unknowns. Or we could similarly have said anywhere that we see VB, we can substitute in 3Vx, you know, whichever way floats your boat. Or you can't do this on the exams, but you could just use MathCAD and solve the system as 4 equations, 4 unknowns, however you want to go about doing it. So I'm going to take a moment to solve this guy for VA, VB, and VC. So let's see. So in my voltage relationship equation, let me clear out all my calculator memory. So we have a 3x3 equation. So I'm going to have 3 VA minus 3 VC. And if I move VB over to the left, or excuse me, to the right-hand side of the equal sign so that all my variables are on the same side, the coefficient of VB is going to be -1. So I have 3 VA minus 1 VB minus 3 VC is equal to 0 for my voltage relationship equation. For the KCL at node A equation, my coefficients for VA are 1/15 plus 1/3. My coefficient for VB is minus 1/3. My coefficient for VC is minus 1/15. And my constant term, sorry, this is equal to 0. My constant term is +2. For my KCL at node C equation, my coefficient for node A is minus 1/15. My coefficient for node B is minus 1/10. Oh, actually, that's incorrect. So my coefficient for node A, or for VA, is minus 1/15 minus 2, because I didn't include the Vx contribution to VA there. So that's why that's that. My coefficient for VB is minus 1/10. My coefficient for VC is 1/15 plus 2. And it's plus because I have minus 2 times negative VC is +2 VC equal to 0. Solve my system. And if I haven't made any mistakes, I get VA is equal to 6 volts. VB is equal to 0. So I feel very strongly that I've made a mistake. And VC is equal to 6 volts. So let me go back through this and try to resolve it.
That's what I got as well.
All right, so let's see where our mistake was made then. So VB is equal to 3Vx. That's certainly correct. And Vx is equal to VA minus VC. That is also correct. KCL at node A, we're going to have VA minus VC over 15. VA minus VB over 3 minus 2. KCL at node C, we have VC minus VA over 15, VC minus VB over 10, -2 Vx. So I think I just punched something into the calculator wrong.
Did you put the KCL at node C equal to? Because I think that might be the problem.
Should be equal to 0. So let's more formally go through these guys to make sure we don't make any mistakes. All right. So our equation VB is equal to 3Vx is 3 times VA minus VC, right? So if I rearrange this, I'm going to have 3VA minus VB minus 3VC is equal to 0. Is everybody okay with the algebra on this guy?
Yes, sir.
Yes, sir.
All right, so that's equation 1. Then I have VA minus VC over 15 ohms minus 2 amps plus VA minus VB over 3 ohms is equal to 0. So that's going to look like 1/15 plus 1/3 VA minus 1/3 VB minus 1/15 VC is equal to positive 2. I just collected my coefficients on VA. I only have one coefficient for VB, so that's straightforward. One coefficient for VC, there's my constant over. So I feel like that one's correct. Then I have VC minus VA over 15 plus VC minus VB over 10 plus 2 VA minus VC, 0. For VA, I have minus 1/15. Sorry, that should be minus 2. Minus 2 VA. For VB, I have minus 1/10. And for VC, I have positive 1/15. Minus 2 times minus VC gives me 2 VC, so plus 2 VC is equal to 0. All right, let's just double check. 3 minus 1 minus 3, 0. 1/15 plus 1/3 minus 1/3 minus 1/15, positive 2 minus 1/15 minus 2 Oh, I'm still getting 6, 0, and 6. So that would mean Vx is 0. What dumb mistake am I making? Let's see. Right now, PA is 6, VP is 0, VC 6. So that would mean the voltage drop over this dependent source is 0, which means the power absorbed by it is 0. So I'm definitely making a mistake somewhere. What dumb thing am I doing? It's got to be something with my algebra somewhere. C minus A over 15, C minus B over 10, minus 2Vx.
Would for node A, wouldn't that be positive 2 amps?
No, it should be -2 because we're taking this current up. So that's why we get VA minus VC over 15. This current to the right, that's why we get VA minus VB over 3. And this current down, which that's why it's -2. Then when we move it to the other side of our equal sign, we have a +2 over here. So that seems fine. VB is definitely 3Vx. I feel like I can't really have screwed that one up too much. So VC minus VA over 15. That is for sure this current flowing up. VC minus VB over 10. That is for sure that current flowing to the left. minus 2 Vx is the current flowing down through that branch. So 1/15 minus 2. Okay, I see what the problem is. The algebra here, I don't have, so it's 1/15 plus 1/10 plus 2 VC. So I forgot the contribution to the coefficient of VC from the middle term there. All right, I was about to have a heart attack and be thoroughly embarrassed about why I can't find my mistake on this problem I've worked probably a dozen times at this point. All right, 1/15 plus 1/10 plus 2. All right, we get VA is equal to 6.768 volts. VB is 0.823 volts. And VC is 6.493.
Dr. Hartman?
Yes.
So I actually got these answers, but they were all negative the first time I did it. Is there a reasoning behind that, or did I maybe put my signs the wrong way for those two?
My best guess is that you got the sign backward on the 2. And I think that would probably flip everything because that's the only known, that's the only constant term in the whole thing.
Okay, thank you.
Yeah, that would be my best guess. All right. So we now have values for VA, VB, and VC that we got by not forgetting one of our terms. You're going to need to know what Vx is. Vx is VC, excuse me, VA minus VC. Which I get to be 0.274 volts. So now that we know this, how are we going to determine the power, let's see, supplied by the dependent current source? Let's start there. So P, this is a voltage controlled current source. So how can we figure that out?
Can you multiply it'd be VC minus 0 times 2Vx.
So VC times 2Vx is absolutely right, because VC is a shorthand notation. Let me erase some of these current arrows here. I didn't mean to erase that. So VC, the nodal voltage, is the same thing as the potential difference between the green node and ground. Since the current of 2Vx is flowing into the negative polarity terminal, you are absolutely correct that our answer should just be 2Vx times VC. Which I get to be 3.564 watts. What about the power absorbed by the voltage controlled voltage source? So we need to know what this current I VCVS is, right? Because the power absorbed, excuse me, supplied by the voltage controlled voltage source will be the voltage 3Vx multiplied by the current flowing into the negative polarity terminal, which is IVCVS. So how can we express that current in terms of other stuff we know?
Well, we know the voltage drops between for VA, VB, and VC. So that means that we know the voltage across the 3 ohm resistor and the 10 ohm resistor. And then we can find the current from there. Then through that,
Yeah.
we can find the current to
Absolutely
the.
right.
Yeah.
So we can apply Kirchhoff's current law at node B, now that we know what all these nodal voltages are, and figure out effectively the current flowing into node B, which I've labeled as IVCVS, must be the sum of the currents flowing out, which is VB minus VA over 3 plus VB minus VC over 10. We could also write it, just for the sake of argument, IVCVS is this current flowing in plus this current flowing in, which may be slightly easier because that would be 3Vx multiplied by negative 2 amps minus 2Vx. Either of those is perfectly fine. We're just, in one case, we're applying KCL at node B. At the other case, we're applying KCL at our reference node, but they're going to give us the exact same relationship. So 3 times negative 2.098. All right, hopefully that example didn't confuse you guys further because of the simple mistake I made. The process was perfectly fine. I just made a simple algebraic error putting numbers in my calculator. All right, any questions or any further questions on this problem?
No, sir.
Cool deal. Then let's get to problem. Oh, was there just the 2 of them?
Sir.
Huh, I'll be dang. Maybe. All right, well, there's only the 2 problems, and I guess we are done for the day unless anybody has any questions or anything regarding any of the homework assignments.
I'm good, sir.
All right. Well, since nobody's saying anything, we finished up today in just a smidge under an hour, so that's okay by me. You guys have a great weekend, and if you have any homework questions or anything that you'd like me to cover in class on Monday, just shoot me an email, and I'll be happy to do it. Thank you guys for participating so much today, and I'll catch you later.
Thank you, Dr. Hartman.
You too. Bye-bye.
Thanks.